Welcome back. We now tackle the third leg in the discussion of classic clustering, where I'll cover some advanced methods. And there is a wide range of advanced methods dealing with clustering, and I will here only deal with two particular ones, K-medoids and spectral clustering. And each of these are, in a sense, qualitatively different from what we've discussed so far. First, K-medoids. What is the idea? The idea is that you minimize the sum of all the observations in a given cluster to the center of the cluster. And the difference with k-means is that now the center of the cluster is not some kind of average of the values for the different observations, but is an actual observation. And so K-medoids you can think of as a particular type of location allocation problem. For example, if you have a number of warehouses and you have to pick a few central warehouses that will supply the other ones, and the objective is to minimize the total distance. Two differences with k-means. It's also a partitioning method, but the center of each cluster is an actual observation, and the objective is to minimize the sum of distances to the cluster center. So the objective function, again, we try to find the smallest value for a given encoder. An encoder, the C that assigns every observation I to a given cluster. We sum over all the clusters the distance from each observation to the cluster center, which is itself an actual observation. This method was introduced by Kaufman and Rousseau in their classic textbook, and they proposed an algorithm called PAM, partitioning around medoids. And the PAM algorithm actually consists of two stages, very similar to what we saw for k-means. The first stage, they call build, is to select k starting points. And then the second stage is swap, is a greedy iterative heuristic that proceeds by considering different swaps of centers for other observations. So if we pick k centers, that means n minus k remaining observations are potential center candidates. And in the swap stage of the algorithm, we assess each possible switch of a current center with one of the n minus k candidates, and then pick the best one and proceed iteratively until we reach a local optimum. Just like with k-means, there is no guarantee of getting a global optimum. So the build stage, the first stage, is just like with k-means, finding k good starting points. And that actually has itself a little iterative procedure. It's not a random assignment. I mean, you could do that. You could take a random assignment similar to k-means. But in fact, in the PAM algorithm, the build stage has a logic to it. So it starts with the center that has the smallest distance to all the other points. And if we have a distance matrix, then that is boils down to picking the observation with the smallest row sum or the smallest column sum. And then once we have the one that is closest overall, so the overall center of all the observations, so to speak, then we pick the next one such that it is closest to the remaining observations. And so we have to think about what happens when some points will remain closer to the first one, and then other points might be closer to the second one. So now we have to pick the second one that is the best in terms of the remaining points and their distances to their current closest centers. Let me make that concrete with our little toy example, same as before. 7 points, here are their coordinates, and the associated distance matrix based on Manhattan absolute distances is in this figure here. And so in each row, we compute the row sum And then we find that for row number 4, or similarly for column number 4, the row sum is the smallest at 24. So we pick that one as the first point. And now we have to find a second point that is as close as possible to the remaining points. Meaning the remaining points, there's always going to be points that are closer to the one we just picked, closer to 4. So now we have to pick a point that makes it better for the remaining ones than what they had with 4. So in this case, it's very simple because there's only one point picked. In general, we look at the distance to the closest center. And we see what happens if we would take another one of the remaining points as the next center. What happens to those distances? And that next point that improves on those distances the most is the next pick. So to make this concrete, in the second row are the distances from each of these points. These are the remaining points, 6 remaining points, to the current first center, the current closest center. In general, later on, these may not be the same centers, but they will be the distances to the closest center. And then for each possible next center point, there's 6 of them remaining, we figure out the difference between the current distance from each point in turn to the current center and what would happen if this next point would be taken as the next center. So would there be an improvement in the sense, is point 1 closer to the new candidate point than it is to point 4? So the distance from point 1 to point 4 is 7. The distance from point 1 to point 2 is 3. So if the distance from point 1 to point 2 is 3, yeah. So if 2 were the next center, then point 1 would move to that center and would actually be 4 distances closer. The difference between 7 and 3 is 4. And similarly, if we consider candidate number 3, what is the distance from 1 to 3? Here the distance from 1 to 3 is 4. So right now we have a distance from 1 to 4 as 7. If 3 would be the next center, then the distance from 1 to 3 would be 4, which is an improvement of 3. And so we do this for each of these candidates. We consider how does the current distance to the nearest center compare to what it would be if each of these row candidates were the next center. And then we pick the row candidate for which the sum is the largest, which means that for all the points taken together, it's the biggest improvement. And the way we get this is because we don't count negatives. So only when there is an actual improvement, so when the distance from this point to the new candidate point is less than the distance to the current closest center, do we count the improvement. If it's negative, we don't count anything. For example, for 5 and 1, if 5 were the next center, then 1 is actually further from 5 than from 4. The distance from 1 to 5 is 8. The distance from 1 to 4 is 7. So there wouldn't be an improvement from having 1 associated with 5, so we enter 0. So think this through. It's worked out with more detail in the lab notes, but it's actually a fairly simple notion. You just see what would be the improvement if for each of these candidate next centers we would pick it. And then we pick the one where the improvement is largest. Then we update this row. Now we would have 2 centers. We update the distance to the closest center, repeat the process, and pick the next one until we have K. Okay, once we have K, and this is a little bit more complicated, how do we improve upon the initial solution? And this proceeds just like in K-means, greedy iteration. We improve, we always make a step that improves, and we take the step that makes the biggest improvement. That's where the greedy part comes from. And the swap procedure, at least as initially outlined in the PAM algorithm by Kaufman and Rousseau, is extremely computationally intensive because it actually looks at all the possible swaps between the K current centers and the n minus K remaining centers. So for each of these K centers, we do n minus K evaluations. So that can very quickly run up when K is large and n is large. So here's the logic. For each current center, so let's say in our example we have 4 and 7, so we have 5 remaining potential centers to swap with. So that means we could swap 4 with 1, 4 with 2, 4 with 3, and so on. Or we could swap 7 with 1, 7 with 2, 7 with 3, and so on. So for each of these, we compute the effect on all the points of the swap. So for every point that is not currently a center, we see what happens if we would swap. And the change in the distance is, we call it C, for each point J. J is one of the n minus K points of a swap between the current center I and a potential candidate center R. There's n minus K of these. Then summing this over all the observations gives us the value of the improvement of the objective function. The objective function is the sum of the total distances. If the improvement is negative, if the total change is negative, we decrease the total distances, so we improve the objective function. As I mentioned, it's greedy, so it takes the swap between a current center and a potential candidate center that improves the most. Okay, let's make this concrete. There's 3 different situations to consider. The first situation, remember, we evaluate this for each point. For each point, we evaluate what happens if the current center, I, is replaced by a new center, R. So I is no longer a center. So we have to look at what happens to J in terms of what it currently is assigned to. So if J is not assigned to I, that means it's assigned to G. So then it could either stay with G, in this case, because it's closer to it. So in that case, nothing happens to the objective function. Or it could move to R. And if it's closer to R than it was to G, then there is an improvement in the objective function. Then the distance between J and the new center R is smaller than the distance between J and its current center G, and so this is an improvement. So we have to look at these 2 situations, and in one case there is 0 change, in the other case there is an improvement in the objective function. So that's the one situation where J is not part or is not assigned to one of the current centers, not one of the centers that is considered for swapping, I should make precise. Okay, what happens if J is currently assigned to one of the centers that is considered for swapping? So we have 3 situations. One is J obviously is closer to I than to anything else. And if J is closer to an existing center than to the new center, then it gets assigned to the existing center. But because it was assigned to I and therefore was closer to I, this does not improve the objective function. In fact, it makes it worse. So we have to count this deterioration in the objective function. In this case, this is what goes on. In the second case, here, we do assign J to the new center. So in the first case, we don't assign J to the new center, but the objective function changes because J is assigned to the second best, so to speak, and therefore the objective gets worse. In case J2, J was assigned to I, but is now closer to R. So it gets assigned to R, however, it is closer to I than to R. So therefore, again, we do not improve on the objective function. And then the third case is the opposite, where J gets assigned to R, but is actually closer to R than to I. So here we improve on the objective function. So in the swap method, we keep track of all these changes and then pick the one that gets the most negative improvement, the largest decrease in the total distances, the total travel cost, if you wish. And so how does this work? And here's a table that kind of spells it out. So we have currently 4 and 7, and we consider a swap of either one of these with 1. So here's the column that matters. Here are the changes in the distance function, the Cj I R. So I is the current center, 4. 1 is the candidate, R, right? So we have here the distance for each of these points, each of the remaining points, to the current center and to the new center, right? So in this case, we see that 2 was assigned to 4, and the distance from 2 to 1 is 3 relative to 6, so we have an improvement of -3. In the case of 3, also assigned to 4, the distance to 4 was 3, the distance to 1 is 4, so that's not an improvement, it gets worse by 1. In the case of 5, again assigned to 4, the distance to 1 is 8. However, 5 would not be assigned to 1. 5 would be assigned to 7, in which case its distance becomes 2. So that gets worse by 1. So remember, this is the case where a point is assigned to the center that is being swapped out, but rather than going to the new one, it goes to the next best solution. And then in the final case, we have point 6 is assigned to 7. The distance to 1 is larger, so it just stays where it is. There is no change whatsoever. There's 0. So then we add all these changes together, and we come up with a total sum of -1. Now we repeat the same logic for a swap of 7 and 1. So we do the same calculations, the same logic. We see an improvement, no change, a deterioration. The value is -2. So between these two swaps, the one replacing 7 by 1 is better, right? And then we do the same thing here, considering replacing 4 by 2 or 7 by 2, 4 by 3 or 7 by 3, and so on. And then we find overall that the greatest improvement is for replacing 4 by 3. So now the new two centers are 3 and 7. And then we allocate the closest observations to those, and we repeat the process. Okay, this is very slow. It takes a long time. A lot of different combinations have to be evaluated, but it's very easy. There's not a lot of computation involved because it's just looking up distances in a distance table. So that's actually fairly efficient. So although, in principle, it's not efficient, it can be efficient for small problems. So Kaufman and Rousseau first came up with a potential solution, and I won't go into detail in the slides. You can find the technical details in the lab notes, but there's actually through 3 classes of improvements to this original PAM algorithm. The first one is called Clara. Clara is really based on a sampling logic. So rather than doing the analysis for all the points, you take a sample of the points and then do the build and swap and find the best solution. And then you take another sample, you keep the best solution in the sample, and then keep doing this. And then at the end, when you stop, you assign all the points to the centers that you found. Of course, if you never sample the best centers, they will not be in the solution. But Clara cuts down on the computation time considerably. Clarence is another method which is based on a combination of a graph theoretic logic and a sampling approach. So the potential neighbors are shown in a graph, and then rather than evaluating exhaustively all the possible swaps, there is a sampling going on of the potential swaps, and it's only done a given number of times so that it cuts down on the calculations. And then in a recent paper by Schubert and Rousseau, a number of fast PAM and fast Clara and fast Clarence algorithms are outlined, which actually cut corners in the build and the swap steps, avoiding redundant calculations, basically. The details you can find in the papers and in the lab notes. So how does this work? Very much the same way as before, but now the centers of the medoids are actual observations. So the center of the clusters, the medoids, are actually observations. So cluster 3, the medoid is here. Cluster 2, it's there. Cluster 5, it's there, and so on. And the results are also presented as such. So for each of the cluster centers, we still have the values, but these values now are not averages, but they are the actual observations, the actual values for the variables for those observations picked as the medoids. We in GeoDa report the Summit square statistics, but keep in mind that that is not the criterion used in the objective function. In fact, the objective function is based on the distances, the sum of the distances to the centers. Within each cluster, the sum of these distances, that is the objective function in the K-medoid approach. And so, in a sense, these sum squares are not, they're useful as a summary of the characteristics of the cluster, but they're not useful in terms of the objective function. So in terms of the objective function, this is what counts, and this is the value that we want to minimize, and rather than maximizing this ratio, we want to minimize this ratio. So we get 0.66 here. Just for the sake of illustration, if we use Clara and Clarence, just like before, sensitivity analysis is very important. And so by running this with the different algorithms and adjusting several of the parameters of the algorithms, we get a sense of how stable some solutions are versus where are the flipping points, so to speak. And we see that the results are slightly different from what we had before. And these criteria get worse. So we try to maximize this. So these two solutions are actually worse than the PAM solution. And they're also worse in this respect, because here we try to get the smallest possible value. We had 0.66. And so see, these get worse. So for small data sets, like the one we use in the Gary example, it's actually not worth doing Clara. Clara, boils down to sampling, so you can never get the same quality result as with the exhaustive enumeration we do in PAM, and then Clarence is somewhere in between. Where these methods really shine is when you deal with really huge problems where just the enumeration involved in PAM is no longer practical. Okay. Spectral clustering is a totally different animal. So far in our clustering algorithms, we have focused on internal consistency, the sum of the distances to the center of the cluster, or a minimization of a notion of variance of the clusters. And these are so-called convex clusters. They're compact in the compact and convex in the attribute space. But what if the data patterns are not convex? And in the machine learning literature, there are some classic example, spirals, moons, Swiss rolls. And the bottom line is that with those type of situations, it's very difficult to find a structure in the data. And the key notion here is that when you project, remember in a lot of this clustering is really about reducing the dimensionality. And when you project these points in multi-attribute space onto the coordinate axes, you don't get good separation. So we have a problem. So this is the spirals data set. It consists of two spirals. This is one, and this is one. So in terms of discovering the structure in this data set, our traditional methods that are based on finding convex, compact clusters don't do very well. I mean, K-means kind of cuts it in two here, and K-medoids cuts it a little bit different here, but neither of them are very good at picking out the separate spirals. And then, of course, if you do it right, and we'll see in a minute that that's not that easy, the spectral clustering picks out those two patterns perfectly. So this is a classic textbook example. Okay, so what is the logic behind spectral clustering? If you paid attention earlier, you would start thinking, oh, spectral, they're spectral again. We're going to be dealing with eigenvalues and eigenvectors, and that's exactly what is the case. So the solution, since the projection onto the regular coordinate axis doesn't do us any good in terms of separating out pieces of the data, we will reproject the data points on a new set of axes, and then presumably on that new set of axes we can discover the separation into subgroups, and then once we have that separated on this new set of axes, we reproject back to the original so we can interpret the data. So it's really very similar, although it's not the same, as clustering on principal components, but we'll see the connection between the two. And basically, it uses eigenvalues and eigenvectors again. So some new terminology. Rather than a dissimilarity matrix, spectral clustering uses a similarity matrix. Now, the one is very easy to turn into the other. For example, if we have a distance matrix, we can simply take 1 over distance, or we can take the maximum distance minus the distance. And the similarity matrix is used at the basis for constructing what is called an adjacency matrix. And an adjacency matrix is something we've already encountered when we talked about spatial weights in the context of spatial autocorrelation. And the way to think about the data, and we've already seen forms of this before, is as a graph consisting of nodes, these are the observations, and edges, these are the connections between the observations. And the strength of the connection is the similarity between I and j. So it's not a distance matrix, it's the opposite of a distance matrix, it's a similarity matrix. And so we'll use this adjacency matrix to find groupings in the data after transformation. It seems a little abstract at first, but I think it will become more concrete. So think of a spatial weights matrix, actually. And so the typical spatial weights matrix has bands, and so there isn't really a clear cut of subgroups. But if you have subregions that are only internally connected and not connected between them, think of this as a parallel with what we were talking about in a clustering algorithm. So internally connected, not connected between themselves, we have a block diagonal matrix. So each of these blocks form a subgraph, and that is an ideal situation where we have so-called connected components. So connected components are connected internally, as in a block diagonal weights matrix, but are not connected with the others. Now, obviously, this is not going to happen in practice very often, and we'll have strong connections internally, but maybe only weak connections with the others, not strong connections with the others. And the way to think about this is just as we would think of the block diagonal weights matrix as dividing the map into two, as dividing the graph into two, we will think of this process of spectral clustering as a graph partitioning process, where we will make k minus 1 cuts in the graph to have k subsets that are internally connected and only weakly connected between them. So that's the concept. We need a few new terms. The degree of a vertex in a graph is the sum of the row sum of the weights. We call this the cardinality of the connectedness in spatial weights. So with this degree concept is a very elementary concept in network analysis or graph theory. We can create a new matrix. So our W matrix is our adjacency matrix. The D matrix is a diagonal matrix with the degree of each vertex on the diagonal as the elements of the diagonal. So the difference between these two, this thing is called the graph Laplacian. And the graph Laplacian is very useful to find properties of the graph structure, and that's why we use it. And typically the graph Laplacian is not used as such, but it is normalized. And there's two broad normalizations that are used in practice. One is basically row standardization that we've seen in the spatial weights. It's also called random walk normalization. And so pre-multiplying by 1 over the degree is the same as dividing each row in this matrix by the matching degree. So if we apply this to the expression for the graph Laplacian, it is the inverse of D times D, which is the identity matrix, minus the inverse of D times the original adjacency matrix. So this is one transformation. The second, this is not symmetric. The second transformation is symmetric in that we pre and post multiply by the square root of the inverse of the degree. So with a little bit of algebra, we find that this is the identity matrix again, but instead of pre-multiplying with the inverse of the degree, we pre and post multiply by the square root of the inverse of the degree. So these are the tools. Then where do we get the maximum separation? As I mentioned already, if this adjacency matrix is block diagonal with k blocks. Now, as it turns out, this is where our friends the eigenvalues and eigenvectors come into play. As it turns out, for a block diagonal adjacency matrix of k blocks, k of the eigenvalues are 0. So in an ideal situation where we have so-called connected components that are only connected to each other and not between each other, then we have exactly k zero eigenvalues. So of course, this is not going to happen in most practical cases. So we're looking for the k smallest eigenvalues of the graph Laplacian. So if we can't get zero, we get to as small as possible. And the counterpart of that, so the graph Laplacian is a difference between two matrices. For that, we find the smallest eigenvalues. With a little bit of matrix algebra, you can show that this is equivalent to finding the largest eigenvalues for the adjacency matrix. So what do we do then in spectral clustering? We first turn the similarity matrix into an adjacency matrix. We simplify it. This is very similar to constructing spatial weights from distance information, as we'll see in a few minutes. So we have our adjacency matrix. We make the normalized graph Laplacian. We find the k smallest eigenvalues and the eigenvectors. And then we apply k-means to the eigenvectors. The eigenvectors are a little bit rescaled. Technical details are in the notebook. But basically the principle is that we get this graph Laplacian, we get the adjacency matrix, we find the eigenvalues and eigenvectors, we apply standard k-means on the eigenvectors, then once we find the results, which is which observations are grouped together, then we translate it back into the original units so that we can interpret our clusters and cluster means, even though the notion of a cluster mean is not that useful because we're really looking at non-convex patterns, these strange things like spirals and Swiss rolls and things like that. So the one piece that I haven't talked about is the adjacency matrix. So we start with a similarity matrix. That gives us a graph structure. We simplify the graph structure by the adjacency matrix. Then we obtain cuts in the graph, which is equivalent to finding the k smallest eigenvalues. So how do we get this adjacency matrix? As I mentioned, it's the same idea as for distance-based weights in spatial autocorrelation analysis. We can use a critical distance, as we've already seen in density-based clustering, that is called an epsilon distance, or we use k-nearest neighbors. K-nearest neighbor weights, as we know, are not symmetric. We can make them symmetric, or we can use a Gaussian kernel density with a given bandwidth, and the bandwidth, rather than specifying k as the number of neighbors, we specify a bandwidth. Many parameters to set. This is not that easy. As you see in the several examples in the notebook, the solutions are quite sensitive to the choice, for example, of k, or to the choice of the Gaussian bandwidth, and the results are always slightly different. So these are two sets of results, and you might say they're the same. They cut the data set in half, but you see the difference here, fewer points. There's a little more points on this end, and there's other small differences. For example, this part is assigned to a different cluster. Here it's this cluster, here it's the other one. So practice sensitivity analysis. The ideal, after a little bit of trial and error, you can come up with the perfect solution, and the specific parameters are given in the notebook. So as I mentioned, the summary statistics are pretty meaningless because they're actual measure performance in terms of compactness. And as you see, the between to total sums of squares is pretty lousy, but in fact, that's what we want, because if we go with a compact convex cluster, then we miss the very special structure of this data. Now, in many applications, when you have tricky groupings in the data, spectral analysis, spectral clustering is the solution. So this concludes my discussion of classic clustering methods. We saw K-means as a partitioning method. We saw hierarchical clustering as a agglomerative hierarchical clustering as a hierarchical method. And then we saw two a little more advanced cases where each targeting a slightly different objective. With K-medoids, it's grouping based on the distance to the center of the cluster. With spectral clustering, it's dealing with non-convexity and very strange shapes in the data set. In essence, changing the problem from clustering on the original data to clustering on the eigenvectors. And as we know from before, the eigenvectors are also the principal components. So this is how all this ties together. In the next and final module, we tackle the introduction of spatial constraints into this problem. See you then.